Hello, everyone. Before I start, I would like to give my sincere gratitude to Professor Yao and to the organizing committee for their great efforts in organizing this amazing forum to share research finding and exchange ideas. It's my honor to have this invitation so I can share our research efforts on modeling multiphase flow. Today, I'm going to focus on application where we propose some simplification in method to drive complex simulation. First, I would like to acknowledge our key researchers who make this research happen. They are our PhD students, as listed here because of time limit. I'm not going to read their name one by one. I would also like to give my great thanks to our collaborators, particularly Professor Ivan Yu, Professor Mary Radman, Dr. Andrew Chris, Dr. Peibo Duan, and Professor Wei Wang. Our research is funded by ARC and the industry, particularly Rio Tinto and Baowu. Our research focuses on multi-phase processes dominated by particles. We have this focus because particulate material is the second largest material handled by human being, followed by largest water. About 70% of final or intermediate products in industry are in particulate form. However, particulate material is a state of matter. To date, how to develop a general theory to describe particle motion has been listed among 125 grand challenges by science. Because of this challenge, we face different problems in phase particles. For example, for particulate systems, we can only achieve 40 even less % of performance of design. This number is much higher for liquid and gas systems, which can reach 90%. We believe computer models can be used to overcome these challenges. Use computer models, we can conduct a simulation over a range of conditions, and the results can be used to visualize complex phenomena in reactors, which are usually black box for multi-phase processes. We can also use the results to generate insights and for design, scale up, process control, and optimization. All this can be done cost effectively. That's the reason now computer models have been increasingly used to study multi-phase processes. Different methods can be used for this purpose. However, for particles, we only have two groups. One is discrete method, where we consider individual particle. The other is continuum method. We consider particle groups or particle assemblies and treat particles as continuous fluid. The model for fluid phase are more complicated. Depending on personal preference and application, we have a range of models like DNS, LDS, and RINS model. In order to simulate the particle fluid flow, we often combine the models for particles and for fluid. This is so-called multi-scale modeling, as demonstrated in the right figure. So here, depending on the trait of the particles, we have subparticle scale model. That's the first one. Here, we simulate fluid details around the particles. And we also have particle scale method. In this approach, particle fluid interaction are described by correlations. Then we have microscale method or continuum method at a safety cell scale, where particles and fluid are treated as continuous fluids. Finally, we have process scale, which focuses on input and output of the equipment or reactors. In our research group, Process Technology Laboratory, PTL, focus on integrated particle technology, mechanistic models, AI technology, and numerical methods to simulate multiphase flow, heat transfer, mass transfer, and chemical reaction, mainly in chemical engineering, metallurgical engineering, and mineral processing. Our research can be considered in 3 levels. The first level, we focus on numerical model and technical development. And in the second level, we use the model we developed to generate insights, formulate the constituent relation, survey, and correlations. And the third level is about application like process optimization, new design, new process development. We also consider problem solving strategy development, software development. Currently, our research priority include low carbon technology, smart processes, and waste management. We have 26 members at this moment, including myself, 6 postdocs, 1 research fellow, or 1 research assistant, 18 PhD students, and 1 master student. So we mainly developed and applied different computer models for specific industry application. Here are some computer code we developed in the past in our group. These are some typical results we obtained from our research. So this animation obtained at the subparticle scale in the left top color, and the particle scale in the right top color. This model are mainly for fundamental research, although we still use this model for some industry application because they are time demanding, can only simulate a small scale. So at the lower part, we demonstrated, we considered different industry scale simulation based on continuum method. Different phenomena are considered in our research, such as bubble generation, droplet generation, particle separation, and reactive flow in different systems. This slide demonstrates some recent results from our group to realize complex system simulation and complex phenomena simulation. For example, circulating fluidized bed and non-spherical particle charging. Then free surface simulation with multiphase, including slag and metal particles, gas. We also made efforts to develop computer model to simulate complex geometry with moving parts. And of course, we consider some complex phenomena, such as particle melting involving gas, liquid, and particle fluid flow. The animation I just introduced are based on mechanistic model. So the results obtained require long simulation time and need a lot of computational efforts. These problems can be overcome using data-driven model, which can provide fast prediction. However, existing data-driven model can largely considered as a black box, and their reliability depends on data quantity and quantity. Therefore, in our research, we also made efforts develop data-driven model and combine with the mechanistic model. So we targeted develop physically enforced data-driven model, which can not only predict overall performance indicators, but also inner states. And the model can provide a fast prediction for optimization and online control. Today, I'm going to introduce 5 cases to demonstrate some unique development which make us to simulate very complicated phenomena. So the first case is iron-making blast furnace. This is a very traditional reactor, but now become more and more important, attract increasing research interest because it has intensive carbon emission, and it's very critical for us to reduce this emission to realize carbon neutrality. And the phenomena inside the blast furnace are very complicated. We have particle, liquid, powder, gas, and many reaction happens under high temperature and high pressure. It's very difficult to use a single method to simulate this system. So in our study, we divided this reactor into 4 regions, and we developed submodel to simulate each region, and this model can be used individually or combined together in an integrated way. Here are some models we developed over the past 10 years, including safety process model for large-scale simulation at the industry scale, and safety DM process model. Here we mainly used for fundamental research. We also have GPU-based burden charging model to consider particle charging at the top, and we have an integrated model to simulate whole particle of whole phenomena in the reactor. We also have some specific model to simulate soft melting behavior. Then recently we developed an AI-driven or data-driven model to predict the inner states in the blast furnace. I particularly feel confident for this safety process model. We have made a continuous and comprehensive effort to develop this model to simulate blast furnace for visualization, design control, and optimization. So this is an in-house code. It has been used by over 15 PhD students and 6 companies. And many unique development have made in the past to realize this simulation. Today, I'm going to share with you 2 key developments. The first is productivity prediction. So during blast furnace operation, raw material is fed into blast furnace according to the stock line as demonstrated in the left figure. So when the stock line reaches the lowest point, we start to charge. And the fade stops when the stock line reaches the highest. The fading rate depends on the inner state of the blast furnace, which are usually related to material properties, operation condition, and the blast furnace geometry. Therefore, productivity is a key factor for industry to determine or evaluate blast furnace performance. However, it had been a long challenge to predict productivity, and there is no clear idea how to establish equation to predict this variable. So in our research, after comprehensive analysis, we realize in blast furnace we have critical information we can use it as a closure relation. That's the coke to all ratio is a constant. And this information can be combined with coke consumption, which can determine it once we simulate blast furnace. Then we can convert these two conformation into coke balance, and use coke balance. We can iteratively adjust the particle fate in the blast furnace, and then we can predict productivity in a steady-state model. So this development provide a solid foundation for us to develop safety process model over the past 10 years. I think this development is very critical. It's very straightforward once we know how to do it, but it's very useful. So the second application we consider, or model development, we consider particle size reduction. So this is a very widely researched topic. Many methods have been developed to simulate this phenomena, such as particle bridge function, population balance model, etc. So in our research, we combine physical measurements with numerical models. So according to our literature study, we found in literature, some research measure particle size reduction under given temperature and reducing gas condition. So that means here we needed this two information. Of course, we also can measure initial particle size. So this initial particle size is used to formulate a correlation to predict the size reduction. However, this also causes big challenge for us to model this phenomena. So in blast furnace, we know when particles move from top to bottom, size reduction happens continuously. So that means particle size reduction happens with history. So the correlation we just introduced cannot be used as it expressed as a function of initial particle size. So to solve this issue, we just differentiate the correlation, and then we calculate particle size change in each cell, and then integrate it to determine the particle size. So in this way, we can use the experimental measurements to simulate particle size. However, in this simulation, we still needed to track particle tracking to obtain particle trajectory. Then we can realize just simulate this mass conservation equation, similar mass conservation equation. However, so this variable can be used to identify particle paths. So by solving this equation, we can give the values to this variable. Then we can identify particle paths at a different location. And along the particle paths, particle size is the same. I mean, for initial size, then we can determine or obtain the information of particle initial size at any location of the blast furnace. So this equation plus this equation together, we can solve the particle size reduction in our model. Here are some typical results. We can say we obtain particle size distribution in our modeling. So with this, we can also consider other effect when it coupled with particle size reduction. So this is the first time we realize this complex phenomena simulation by combining mathematical modeling and the physical experiments. So in the third case, or in the second case, we consider reactors filled by large biomass particle in cement industry. So this large biomass is used to replace coal to reduce carbon emission. However, this causes a problem because large biomass has a temperature gradient inside the particle. This can result in incomplete burnout readily. So far, we don't have any tools can be used to effectively guide the use of large biomass for this reactor. For this reason, we develop a comprehensive model. So in this model, we consider particle agglomeration, and we also consider particle temperature gradient effect for the large biomass. So this modeling is quite straightforward. First, we simulate a single particle, use a partially resolved simulation method. That's direct simulation. So we can obtain the temperature distribution inside the particle. Then we simulate a particle, just ignore this temperature gradient. By comparing the results from these two models, we can establish or determine the corrected factors, and then modify this model without consider particle temperature gradient. As this model is computation efficient, and this spatial resolve method is very time demanding. So the idea is quite straightforward. However, so in this process, when we used to establish the correlation to determine the corrected or correction factor, we needed to identify different mechanisms for reaction kinetics for heat transfer and material properties. It's very important to identify their different contribution and develop correction factor for each of them. So this is the key for us to successfully to develop this reliable method to consider contribution of temperature gradient in large biomass and their effect on the process performance. So here are some typical results demonstrate our model is reliable. Here we validate our model for single particle reactor, multi-particle reactor at a lab scale, and we also consider industry scale reactor and demonstrate good prediction. So in the third case, we consider modeling non-Newtonian suspension flow. As we know, for non-Newtonian fluid, the relationship between shear stress and shear rate are nonlinear. And there are many types of non-Newtonian. At this stage, we don't have a general rheology model to describe the relation between shear stress and shear rate for different non-Newtonian fluid. So that means we have to consider long-Newtonian fluid specifically. So this cause challenge. As the knowledge we develop for one long-Newtonian fluid cannot be extended to another one. So that's the reason for many long-Newtonian fluid, we don't have a general turbulence model. We don't have drag force model. So in our research, we made the efforts to develop a computer model to formulate drag correlation to simulate turbulence. Given rheology model is known, of course, there are big gap to develop rheology model to describe different fluid rheology. So here is our strategy. You can see again, we use multi-scale modeling strategy. We use the subparticle scale to formulate the particle fluid interaction force. We use DNS to simulate the fluid turbulence for long-Newtonian turbulence flow, and then we simulate the particle fluid flow. For subparticle scale model, we develop two types of model. One is based on traditional finite value method coupled with DEM. We also develop a model coupled with DEM using lattice Boltzmann method, as this method is computationally efficient and it's quite simple. Use the computer model at the subscales. We made a systematic effort to establish drag force model. Here I just listed the effort we made to develop such a model through a PhD project. First, we consider single particle and two particle. Then we consider effect of particle bed with long-Newtonian rheology. And then we consider particle bed structure, particle size distribution. And then we examine effect of particle dynamics on the drag formulation. As in all this research, we first treat particle as stationary particles. Through this effort, we establish a drag force model as demonstrated here. However, this drag force model just for power law fluid. This is the simplest fluid rheology. Then we move to more complicated application. That's mining tailing, which become very important for Australia, as our country is a source-based country, and the mineral export represents major export income in this country. How to manage mining tail is very important for this country. And for mining tailing, the rheology model could be power law model and the Herschel-Berkeley model. So that means the model we just developed to describe drag force in power law fluid cannot be used anymore. So straightforwardly, we should redo all our simulation through our PhD project. So this is time demanding. It's not allowed in our research. Here we introduce some simplification. Of course, we made efforts to develop our unresolved DNSD model to simulate long-Newtonian fluid flow. Here we established this model through 4 steps. First, we consider Newtonian fluid flow for DNS simulation, and then non-Newtonian fluid flow, and then we consider Newtonian suspension flow and non-Newtonian suspension flow. Particularly in this development, we simplify the efforts for drug force formulation. According to our previous research, drug force formulation mainly focus on two parts. The first part is establish the rheology effect on single particle. And then in the second part, we consider contribution from labors. So with this in mind, we just we combine the drag force for single particle and with the model consider porosity. So in this way, we can simulate the drag force without much simulation. And we demonstrate this method is working through our model validation. We use the physical experiments from our collaborators. So here as more comparison to demonstrate that our model is useful. So in the fourth case, we consider a modern non-spherical triple charging phenomena. In the past 20 years or so, we made a continuous effort to model particle transportation, consider different phenomena as demonstrated here. So particularly for non-spherical triple charging, here we needed to calculate the particle void fraction. So in the safety DM model, and we also did consider the effect of particle shape for the drag force model. So for void fraction, we just use divided method. So this is quite straightforward, widely used for spherical particle, and I think it can be extended for non-spherical particle readily. And more importantly, in our research, we use the different method to smooth the solid body fraction calculation. So here we can use different method like the calculation based on spherical particle, spherical cells, multigrade, and solving diffusion equation. So in our this research, for parallel efficiency, we use diffusion method. And more importantly, in our study, when particle occupy the whole cell, needing zero solid fraction or even negative values, we just keep there and we solve this equation. So in this way, although the results before smooth remains physically meaningless, however, we can keep the results have mass conservation after the smoothing, and all the results follow the physical meaning. So in this way, we can ensure our simulation correct. Also, in the drag force modeling, we can combine the drag force model for single non-sphere particle with the correlation consider effect of labeling particle. So in this way, we can establish a reliable model to simulate the effect of particle shape. So here we demonstrated our model can predict the physical measurements under different conditions from particle system to fluidized bed and particle charging. So in the fifth case, we consider AI or data-driven model. So in data-driven model, we targeted models can mitigate their reliance on data quality and quantity and processing. So that's some simple idea I wanted to demonstrate it here. So in this study, we try to develop optimization algorithm. And in traditional optimization method, if we wanted to do the optimization, we normally first establish a prediction model based on dense data in the domain we consider. So the data is more dense, the prediction is more reliable, and then the optimization is more reliable. So this require lots of effort for data generation. To minimize such effort, we produce a new method. First, we establish the prediction model based on sparse data set. And in use this model, we can determine the error containing the optimal results. Then we move the domain, which is much smaller than the original one, and establish a prediction model with dense data, because the domain is much smaller. Then the effort used to generate data for develop prediction model is much less. So in this way, we can significantly reduce the requirement for the optimization method for data generation. Then use this method we demonstrated, we can realize multi-objective and multi-variable optimization. Here we apply this model, design a new hydrocyclone for particle separation, and improve this cyclone significantly in terms of separation efficiency and energy consumption. Okay, now come to the end of my presentation. Here is my conclusion remarks. Multiphase processes are inherently multi-scale and multi-phase case, so make them difficult to quantify. So in our research, we develop multi-scale and multi-physics model to simulate these complex systems. We always try our best to propose some simplification to realize complex simulation. So in this development, we believe the interdisciplinary knowledge and a good understanding of the underlying physical mechanisms make our development possible. This is all my presentation. Thank you for your listening.
Yeah, thank you very much. Very good job. Yeah. Actually, your presentation, the time actually is very short. I'm thinking you give us a lot of information about their simulations, many different models, many different physics. So, yes, quickly, I'd like to give you the questions first. We have two parts questions. Yeah, some of the questions actually come from the web or the other platform. Yeah, because you know this video simultaneously, yes, can be seen by other places. So at first, I like to give the questions by other people. I'm thinking the question is very difficult. What is the core definition of creative simplicity in multiphase process modeling? Can you please give this question?
So Yeah, so in our modeling, so basically, if you want to simulate a complex phenomena, we often first establish some constitutive relation at a lower scale, and then we integrate this constitutive relation to higher layer until we can simulate the whole system. So normally we should do step by step to establish all the reliable constitutive relation. But this sometimes or in most situations are impossible. So in this situation, we should just introduce some simplification. For example, we borrow some idea in this upscaling process from other study. One example is our drug force formulation for Herschel-Berkeley flow. If we follow a standard procedure, we have to go through a 3-year project to formulate a drug force model. It's almost repeat our previous PhD project. I think that's impossible. So, however, so in our study, we found if you just simply combine two modeling effort, you can realize reasonable simulation. And then in our study, we found the correlation for single particle and for the correlation of porosity. We combine these two together. So that's already good enough for our simulation. So obviously here we don't have clearly a definition of what about the simplification. Here I more mean is we should like try to save efforts to establish a model reasonably represent physics, but good enough to predict the results according our to handle our application.
Yes, actually, this question is very good. And at the beginning, I also have a similar question, but it's simpler because for example, page 15, you just assume a steady state model to in order to save computer time, and to replace this turbulent or very complex flow in the reactors. So this is also my question, but this question actually is similar to this question, but this guy's the question I'm thinking is very very simple, it's very short, but very important. And
Yeah,
just
that's right. Even for this model. I mean, the idea is very simple. At the very beginning, nobody think you can like establish a method to predict productivity. So if you want to productivity, you have to develop unsteady state model. So this is very time demanding. Even steady state model, it can take about 3 days if we use over 100 CPU. If you simulate the unsteady state, it's very time demanding. So that's the reason we try to develop a simple method to realize this simulation. Then we finally, with this little information, and then we convert it to cobalance, and then we can predict this K variable very confidently.
Because it's very difficult to give us some. You give us some simply say or assumption for your communication, but what is this code? This method or the rule, how to judge it, and especially for some new guys or new research fellow go into this area to consider some very complex industry problems, how to simplify the problems to our academic or just now you mentioned, yes, to save the computational time. I'm thinking it's very difficult for us to judge it. So I'm thinking your experience or your idea for these areas is very important for us to learn actually. Yeah.
Yeah, that's right. But probably because we still have time, I give a little bit more information about this modeling. This represents a very, very important foundation for our blast furnace model. You can say in blast furnace, we need to add coke, that's as a reduction agent. And then we have iron ore, we feed it into the blast furnace. Then during operation, coke is consumed by reaction, and the iron ore is reduced to iron and melted into liquid. So now how much iron ore should be added into this blast furnace really depends on lots of variables, and it's unknown. However, in this operation, coke and ore is always charged into blast furnace at a given ratio. Now in our simulation, we first do the simulation. We calculated every consumption of coke. And then we finally, after we get all this consumption, we sum them together. Say if they are equal to the coke loaded into the blast furnace. If it's too much, or if it's larger, then we just reduce the feeding rate. Otherwise, we increase the loading rate. Then use this coke balance, we can also determine the adjustment rate for next iteration. So in this way, we can determine the productivity after a number of adjustment. That's allow us to determine the final feeding rate that's corresponding to productivity. I hope now my explanation is clear. So the idea is based on our understanding of this process. Of course, we need to know some modeling technique. So combine this, we can simplify this modeling to realize this simulation of difficult phenomena.
Okay, thanks. And another very good question from the group, from the WeChat, outside the platform. The second question is, from the physical and chemical nature of multiphase processes, what core parameters, interactions, or space-temporal scales are typically prioritized for creative simplification? What are the theoretical basis and the priority judgment criteria behind this trade-off?
So honestly, there are no standard method to propose simplification. I think when we do this kind of model development, we must very carefully understand the physics behind, and we must understand the numerical technicals very, very clearly. And then we combine these two together to simplify the modeling procedure. So I can only say like this. So in the past years, all this kind of unique development from our research is really based on a long accumulation. For example, for this phenomena, before I work on this, our research group working on this phenomena, try to overcome this issue, and I spent nearly 4 years got nothing. So then I worked on this for nearly 2 years. Finally, I found this solution. Even we develop a model simulate all the complicated phenomena in the reactor, but we can't predict this productivity. Even now, I publish this method, and the people sometimes feel difficult to understand what I'm talking about.
Yes, you are right. So that's our uniform and criteria or rules for all of these processes. Different cases have different story and different physicals and chemical cases. Yes.
Yeah, that's right. Yes, definitely. You need a deep thinking, and yeah, when model developer, like every minute and think about how to find a good idea to realize some difficult simulation. Even for the like particle size reduction. Although here I just mentioned this, just use 3 lines to demonstrate this idea. Actually, this take nearly 1 year, and with like collaboration between 2 PhD students and myself. So we like 3 together, each of us proposed like a part of the model. For example, I identify the method to use like differentiation, like get this derivative form of the equation, and then another student proposed this method to track the particle path line, and then the third PhD student implemented this method, and there are lots of other considerations.
Okay, and I have another. The last question actually is regarding some fundamental theories regarding this drag force. You from your presentation, you give this drag force for the long spherical particles. I don't know. Yes, we usually just consider the spherical particle. So can you please give a very briefly the key difference between the two parts? Or you should say for the long spherical particles, what's very important to the for the drag force? You know, drag force actually is very important to for the particle behavior. Actually, yeah. Can you please give us some very short brief or
So,
introduction of this?
so for the drag force,
Yeah.
honestly, this is a method widely used in literature. It's not from our research group, but I just find this idea is quite good. It's
Yes.
quite alive with what we have done.
Yeah.
So in this model, you can say the drag correlation coefficient is different. It considers particle direction or orientation. But normally in for sphere particle, we don't have this variable. But for long sphere particle orientation is very important. It can significantly affect the value of drag force.
Okay. Thank you. Actually, the time actually is very near this first the section, and thank you very much for very good their presentations. Actually, I'm thinking other people have some many different questions, and we will ask the people connect with you by email or for futures connection. Yeah.
Yeah, definitely. I'm happy to answer.
And also just now I mentioned that after this presentation, we will transfer your PDF, this presentation stuff to all of these attendees on the website and provide it for other people's for the reference. Yeah.
Yeah, thank you.